Here we shall solve some KCET previous year questions on the chapter Kinetic Theory of Gases. Mm, uh, so if you have any questions in the solutions or any other doubts if you have, then please write that in the comments section. We shall clarify them in the subsequent videos. And if you feel that you have more difficulty in any of the chapters of physics, then also please mention the name of that chapter in the comments section. Then we shall give more priority on it and solve more and more questions on that particular chapter. Uh, uh, Also, the homeworks on every chapter will be uploaded in the Sapience Education application. So please install our Sapience Education application, whose link has been provided in the description. So here, this is the question number 1. It is told that a monoatomic gas is suddenly compressed to 1/8 of its volume adiabatically. The ratio of its final pressure to its initial pressure is given. The ratio of specific heat of the given gas is 5/3. So the ratio of specific heat, that is gamma, which is equal to Cp by Cv, that is equal to 5/3. This is given. And for an adiabatic process, we should have PV power gamma, that is equal to constant. So it means P1 V1 power gamma, that is equal to P2 V2 power gamma. So now it is told that the monoatomic gas is compressed to 1/8 of its initial volume. So V2 is V1 by 8. If I take V1 is the initial volume and V2 is the final volume. So therefore, this is given, and it is being asked to find the ratio of the final pressure to the initial pressure. So P2 by P1 has been asked. Now therefore, P2 by P1, that is equal to V1 by V2 whole power gamma. P2 by P1, that is V1 by V2 whole power gamma. So from here we see that V1 by V2, that is equal to 8. So P2 by P1, that will be equal to P1 by P2, which is 8 power gamma. So gamma is equal to 5/3. So 8 is 2 power 3. So 2 power 3 whole power 5/3. So the 3 and 3 will cancel. So this is 2 power 5, which is 32. So option A is the correct answer. Then it is told during an adiabatic process, the cube of the pressure is found to be inversely proportional to the 4th power of volume. So this is given for that adiabatic process. So then the ratio of the specific heats is asked. It means that we have to find out gamma, which is Cp by Cv, which is the ratio of the specific heats. So from here we can say that P power 3 into V power 4, that is equal to constant. So therefore P cube V power 4 whole power, if I do 1/3, that will be also constant. So then we can say that P into V power 4/3, that is equal to constant. So therefore we know that this should be equal to PV power gamma. So therefore gamma should be equal to 4/3, which is equal to 1.33. So option B is the correct answer. So in any of the solution steps, if you are unable to understand or any other doubts if you are having, then please write that in the comments section. It is told that if gamma is the ratio of the specific heats, so gamma is Cp by Cv, and R is the universal gas constant, and the molar specific heat at constant volume is given by Cv is how much. Okay. So we know that Cv that is equal to f by 2 into r, and we know that Cp minus Cv, that is equal to r actually. Since Cp is equal to Cv plus r, which is equal to f by 2 plus 1 into r. So Cp minus Cv is r and Cp by Cv is gamma. So therefore Cp is equal to Cv into gamma. So therefore if we place it here, then if we substitute the expression for Cp here, then we will get Cv into gamma minus Cv, that is equal to r. So therefore we can say Cv into gamma minus 1, that is equal to r. So therefore Cv will be equal to r by gamma minus 1. So option A is the correct answer. And here it is told the temperature of a gas contained in a closed vessel. The temperature of a gas which is contained in a closed vessel of constant volume. It is having constant volume. The temperature of a gas contained in a closed vessel of constant volume increases by 1 degree Celsius when the pressure of the gas is increased by 1%. So here the volume is constant. It means that it is an isochoric process. Now we know that PV equals to nRT for any ideal gas. For any ideal gas, we can apply the ideal gas equation. So therefore it means that if V is constant, then we can say that P is proportional to T if the volume is constant. So now therefore I can say that P1 by T1, that is equal to P2 by T2. Now here it is told that the temperature increases by 1 degree Celsius. Suppose the initial temperature was T1. Initially suppose we say that the temperature was T1 and the pressure was P1, and finally the temperature increases by 1 degree Celsius. It means the temperature is T1 plus 1 degree Celsius. So it means that when there is increase in 1 degree Celsius, it means in the Kelvin scale also the increase is 1 Kelvin. So the initial temperature was T1 Kelvin, the final temperature will be T1 plus 1 Kelvin. Since 1 degree Celsius increase means 1 degree Celsius increase in the Celsius scale, that also is equivalent to 1 Kelvin increase in the Kelvin scale. So, and the pressure is P2 suppose. So P2 is the pressure of the gas increased by 1%. It means that it is P1 plus 1% of P1. So then we have to find the initial temperature, that is T1. So therefore P2 will be P1 plus P1 by 100. That means it is 101 P1 by 100. So therefore we can see that P2 by P1 that is equal to 101 by 100. Now therefore T2, so T2 is T1 plus 1. So now we see that P1 by T1 that is equal to P2 by T2, and P2 by P1 we have found that is equal to 101 by 100, 101 by 100, and T2 that is equal to T1 plus 1. So then if we substitute that, then we will have, so T2 by T1 that is equal to P2 by P1, which is equal to 101 by 100. So T2 is T1 plus 1 by T1, that is equal to 101 by 100. So therefore I can say 1 plus 1 by T1, that is equal to 101 by 100. For 1 by T1 is 101 by 100 minus 1. So that will be equal to 1 by 100. So therefore T1 is 100 Kelvin. T1 is 100 Kelvin, or we can say it is 300 and 100 Kelvin means, so 273 Kelvin is 0 degree. So 100 Kelvin means it is minus 173 degrees Celsius. But so 100 Kelvin is the answer. So option A is the correct answer. it is told a perfect gas at 27 degrees Celsius is heated at constant pressure so as to double its volume. A perfect gas is there which is heated. So a perfect gas is there. Its initial temperature is 27 degrees Celsius, and it is heated at constant pressure. So the pressure is constant. It means that it is an isobaric process. It is it is heated at constant pressure so as to double its volume. Its volume is doubled. So the initial volume, suppose it is V. Initially the volume was V. Initially the volume was V, and the temperature was 27 degrees Celsius, which is equal to 300 Kelvin. And the finally the volume is 2V. It is 2V. Since the volume is doubled, then the increase in temperature of the gas will be, so suppose T2 is how much? So we have to find the increase in temperature. Therefore the increase in the temperature will be T2 minus T1. So that is being asked. Since we know that PV equals to nRT, which is the ideal gas equation, so when pressure is constant, we can say volume will be proportional to the absolute temperature of the gas if the pressure is constant. So then we can say that V1 by T1, that will be equal to V2 by T2. Since by V by T, that will be constant. So therefore volume initially that was V, and T1 initially that was 300, and V2 is 2V, and T2 we have to find. So V and V will cancel out. So T2 is equal to 600 Kelvin. So therefore the increase in temperature, that is T2 minus T1, that is 300 Kelvin, and which also is equal to 300 degrees Celsius. Since why the increase in temperature in Kelvin scale is same as increase in temperature in the Celsius scale. So option D is the correct answer. Okay. Then it is told the mean energy of a molecule of an ideal gas is. So we know that the average kinetic energy per molecule of an ideal gas per degree of freedom per degree of freedom per molecule, the average kinetic energy of an ideal gas, that is half kT, where K is called as the Boltzmann constant. So there are 3 degrees of freedom. So there are 3 degrees of freedom. So we can say that the average kinetic energy per molecule of the ideal gas, since why there are 3 translational degrees of freedom, and since the size of the molecule is considered to be negligible, so there are no rotational and or vibrational degrees of freedom in case of an ideal gas. So the kinetic energy per molecule of the ideal gas, that will be equal to 3 by 2 kT. So option C is the correct answer. Then in question number 7 it is told pressure of an ideal gas is increased by keeping temperature constant. So the pressure of the ideal gas is increased by keeping temperature constant. The temperature should be kept constant. Then the kinetic energy of the molecules, will that increase or will that decrease, or will it remain same or increase or decreases depending on the nature of the gas? So which option is correct? We have to find it. Okay. So pressure of an ideal gas is increased by keeping temperature constant. So we know that PV, that is equal to capital N into KT, where K is Boltzmann constant and N is the number of molecules of the ideal gas. temperature is kept constant, so the kinetic energy of molecules, that is equal to into n into 3 by 2 kBT, is 3 by 2 nkt. Temperature is kept constant and pressure is increased. So this is 3 by 2 nkt. So temperature is constant, so it means n, and n is also constant since it is n is the number of molecules. So since temperature is kept constant, so P into V, that will be also constant. So even if pressure is increased, the volume has to decrease so as to maintain the constant temperature. So the kinetic energy, that will be 3 by 2 into P into V, or I can say 3 by 2 nkt. That will be constant if the temperature is constant, if T temperature is constant. So it will remain the same. So option C is the correct answer. Then in question number 8, it is told 1 mole of oxygen gas is heated at constant pressure. 1 mole of oxygen gas is heated at constant pressure starting at 27 degrees Celsius. 1 mole of oxygen gas is heated at constant pressure. It means the initial temperature was 27 degrees Celsius, which is equal to 300 Kelvin, and the pressure is kept constant. So how much energy must be added to the gas as heat to double its volume? How much energy should be added to the gas so as to double its volume? So we know that PV equal to nRT when n is the number of moles of the gas. So it is called as the ideal gas equation. It should be followed by any ideal gas under any condition. So therefore the pressure is kept constant. So therefore V should be proportional to T, since pressure is kept constant, since it is an isochoric process. So therefore we can say that V by T is constant. So V1 by T1, that will be equal to V2 by T2. So from here we can find the final how much energy must be added to the gas to as heat to double its volume. So the final volume V2 is 2 V1. The volume is doubled. So therefore we can say V1 by T1, which is 300 Kelvin, that is equal to V2, that is 2 V1 divided by T2. So T2 should be equal to 600 Kelvin. T2 is 600 Kelvin. Now how much energy should be supplied? So therefore now the heat that should be absorbed by the gas, heat that must be added, the amount of heat energy that must be added to the gas under constant volume, that should be equal to NCP delta T. NCP delta T, since heat is added under constant volume. Since the heat is absorbed at constant pressure, it is absorbed at constant pressure. So at constant pressure the specific heat is given as Cp. Now therefore it is 1 mole. So 1 mole, and for oxygen gas the degrees of freedom, for oxygen gas the degrees of freedom means the number of degrees of freedom, that is equal to 3 translational degrees of freedom and 2 rotational degrees of freedom. So it will be 5. So F is equal to 5 actually. So we know that Cp that is equal to F by 2 plus 1 into R into delta T, which is T2 minus T1. So this much in joule it will come. So therefore that will be equal to the heat, the required amount of heat, that is N into Cp, which is 5, it is 5 by 2 plus 1 into R into, that is 600 minus 300 is my joule. So this will be 7 by 2 R into 300, 7 by 2 R into 300 joules. So 3 7, so 150, so 150 into 7 7 1050 R, 1050 R joule. So option C is the correct answer. Then we shall solve our last question of this chapter on kinetic theory of gases. Then it is told that a certain amount of heat energy is supplied to a monoatomic ideal gas. One monoatomic ideal gas is there. Suppose, for example, helium suppose. So a monoatomic ideal gas which expands at constant pressure. It is expanding at constant pressure, so the pressure is constant. It means certain amount of heat energy supplied. Heat energy supplied, that is delta Q, and that will be equal to NCP delta T. Since why at constant pressure only the heat is supplied, and it expands. Supplied amount of gas which expands at constant pressure. So the volume increases. V1, this is V2, so V2 is greater than V1. What fraction of heat energy is converted to the work? What fraction of heat energy is converted into work? Okay. Certain amount of, so the amount of heat energy that is supplied, that will increase the internal energy, and that will do some work also. So delta Q, we know that is equal to NCP. What fraction of the heat get converted to the work? So it means that W by delta Q, that is how much. This fraction is how much, that we have to find. The fraction of, what fraction of the heat get converted to the work. So NCP delta T will be equal to, this is NCV delta T. Delta U is NCV delta T. V, volume is constant. Volume is constant. Volume. So if the volume is kept constant, that okay, then the whole amount of heat will go into the increase in internal energy only. So it is NCV delta T plus work done. Okay. Work done, that will be, so when pressure is constant, then work done is equal to P delta V. So work done equal to P delta V when, this is work done, okay, when pressure is constant. So now PV equal to nRT, so I can say that W will be equal to nR delta T, that is equal to P delta V. So now therefore we can say that, so therefore W by delta Q, that will be equal to nR delta T. Also from here we can see that W will be equal to N into Cp minus Cv into delta T. So Cp minus Cv is always equal to R. So that will be also nR delta T. So in this way also we can see that the work done under constant pressure should be nR delta T. So nR delta T divided by N Cp delta T, which is N into F by 2 plus 1 into R delta T. Cp is equal to F by 2 plus 1 into R. Okay, so R delta T will cancel, and N will cancel. So this is 1 by 1 plus F by 2 So this will be, so now the degrees of freedom. So the rule is that for a monoatomic ideal gas, for a monoatomic ideal gas, the degrees of freedom, the number of degrees of freedom, the number of degrees of freedom, which is F, that will be equal to 3. So now therefore, the required fraction, the fraction of the heat energy that is converted to the work, the fraction of the heat energy that is converted to the work, that is converted to the work, that will be equal to W by delta Q, that we have found it is equal to 1 by 1 plus F by 2. So that will be equal to 1 by 1 plus 3 by 2. So which is 1 by, this is 5 by 2. So that is equal to 2 by 5. 2 by 5. So option A is the correct answer. So hope you have understood the uh, solutions of all these 9 questions on kinetic theory of gases. And in case if you have any other questions on in any of the steps of the solution, or any other kinds of doubts if you are having, then please write us in the comments section. We shall clarify them in the subsequent videos. And please install our Sapience education application, whose link has been provided in the description, um, where we shall upload some more KCET homework questions on every chapter, which shall be very much helpful for your KCET exam. So here we shall end our class on kinetic theory of gases. So thank you everyone.